let's talk about potential energy graphs. So here I have graphed a potential. Here's a potential. This is a potential energy I have as a function of position. So you can see here I have more potential energy, here I have less potential energy, here I have more potential energy again. This could be a function of height, for instance, because potential energy can equal mgh. If this was just a graph of elevation in a gravity field, this height graph would be the same as a potential energy graph. So how would an object behave in that potential? Let's see. We see that an object with this much energy will go back and forth between this point and this point, which we call the classical turning points. Why? Well, because that's where it turns around. We also notice that as it comes down here, it loses potential energy, and that changed to kinetic energy. We also notice that if we give it more energy by starting it up higher, or by pushing it with more kinetic energy, it both goes to a higher potential energy for a turning point, and it gets going faster at the bottom because it has more kinetic energy. And so let's take a look at these definitions. This would be, for instance, my total energy, energy total. And this is constant in time and in space. The total energy is the same all along, back and forth. But the potential energy drops. So this is the kinetic energy, the difference in the two. This is not really new to you because we did those roller coasters where we showed the ones that end the lowest have the most kinetic energy simply because the potential energy has dropped the most. Now over here, this is an interesting spot. This is where the potential energy is greater than the total energy. So here, the kinetic energy is less than 0. So these are unallowed regions. You'd call that classically unallowed. These points here are where the total energy is equal to the potential energy. So the kinetic energy is 0, and velocity is 0, and this is a turning point. So this has two turning points here and here, and down at this point is where I have the greatest velocity because I have the least potential energy. Potentials don't always have to be gravitational. What if we had a cart on an inclined track? Then we recognize that the potential energy of the cart would be equal to mg delta h. Okay, this is a gravitational potential. But what if on this side there was a spring? And we had some delta x right here. And we'd see that, oh yeah, the potential energy of the cart would get much greater as we compress the spring. The potential energy of a spring is equal to 1/2 kx squared. And so this potential energy would rise up very quickly right here. And so when we add the two, we'd have a potential energy graph that looked like this, and then here rose parabolically, where this curve is the sum of the parabola and this continuing decrease in elevation. And so what you'd have is you'd have a cart that would move from this potential, and it depends on how much energy it have. Let's say we started it here, so its total energy was this much, and it would move down and then hit the spring. Like this, so it would move in x, along x it would move somewhat like this. Faster, bounce back. Faster, bounce back. Okay? The potential energy would decrease. This would be the lowest point of potential energy, and we'd have another classical turning point here. This would be the highest velocity, where you have the lowest potential between the slanting downward and the compression of the spring. And that's where the kinetic energy would be the maximum, and you'd have your highest velocity. It would look something like this. And for a higher energy, we start at a higher elevation. And it would compress the spring further before it got to its turning point. And it would go higher on the ramp until it got to its turning point. So we know about turning points, we know about the classically forbidden regions out here, and we know that the maximum velocity is where the potential energy is the lowest. There's two more things. What about the force that an object feels? We know that if we put the mass here, it's going to feel a force in that direction. If we put the mass here, it's going to feel a force in that direction. And so the force on a body doesn't depend on its energy, it depends on the slope. The force of gravity pushes things downhill. The force of the spring will push you to a lower energy state. And this is easy to show because we know that work is equal to force dot dx. The work is a change in energy, and this would be force in the x direction times delta x. Right? Plus force in the y direction, delta y, force in the z direction, delta z. But let's just look at one dimension. Then we can divide through, and we have change in energy over change in x is equal to the force in the x direction. And so what this tells us is that the force I feel right here from this gravitational potential change is equal to the derivative of the work that I have to do, how much work I have to do to increase this energy for this distance. So that's the slope of this line. The force that the potential puts on me is equal to the opposite of the force that I put on the potential. If that's the force that I have to put on the object to keep it in the potential, then the force that the potential is putting on me is in the opposite direction. And so what we say is that the force provided by the potential is equal to the negative gradient of the potential energy. This is a vector, and this is a vector. This is a gradient operator. It's d dx in the x direction plus d dy in the y direction plus d dz in the z direction. Okay, we're only going to deal with one dimension, and so it's enough to say the force in the x direction is equal to the negative slope of the potential energy curve. That's negative d potential energy dx. Okay, if you forget that, just remember, things flow downhill. Downhill means to a lower potential. And how hard things want to go downhill isn't determined by how high they are. It's the slope of the line. The more steep the slope is, change in potential energy over change in distance, the greater the force is going to be pushing it down that hill.